Alright, welcome back to the challenge. ARM exceptions, gotta catch them all. In this video series I'll try to trigger as much exceptions as possible and catch them. In the previous video we made a start with this and we were able to trigger 3 exceptions. The sysdig, the pentsv and the sv call. And at the end of that video we tried to trigger the usage fault, I believe, but that didn't work quite yet. And I wanted to have GDB, but I didn't have that available at the time. So in the meantime I've installed that. So let's see, let's continue. Maybe recap what we have. So we have our development board that can run our program. Our program is currently the following. We print hello world. We do some setup of the priorities. Then we do some set of the priorities. Then we start the sysdig, and here we wait until the sysdig triggers and all our other exceptions, and the last one will set the done flag if everything goes according to plan, and then we'll see the end message. But I think currently that's not the case because we're still hanging somewhere. And the idea is that the sysdig triggers, this will set the pentsv flag, so the pentsv will trigger, that will set the sv, that will do an sv call instruction, that will trigger the sv call, that will do an undefined exception, of an undefined instruction, and that should cause the usage fault. And when we're in the usage fault, it's currently our last exception. Then we set the done flag and everything should unwind, and we end back in the main, fall through this while and see the end. Okay, let's see if this works. Do cargo run. And currently, this is where we left the previous video, this doesn't work. We see the sysdig. And yeah, that was the other thing. We leave the sysdig, then we enter the pentsv. So then the sv call, that's working according to plan. But here we don't see the usage fault. So yeah, currently I'm a bit unsure what's going on. So let's attach a debugger and look at it with GDB. So we abort this. Off stream I did it already to check it out, but this is the command. We start the ProPRS with GDB server and the chip that we're targeting, that we can run, and in the other window I can start GDB and should be able to attach to the target, target remote, I think it was Andri. Alright, Andri, click save. Sure. Okay, and now we can do a backtrace. And if we start from here, yeah. So we see the main, we see the pentsv, we see the sv call, and now we see a HardFault. So it seems that we entered the HardFault instead of the usage fault that we wanted. So first, let's add an exception handler for the HardFault. So at least see that this happens. HardFault, and let's update this as well. Yeah, HardFault is later in the list, or higher up the priorities. So here it is. So we will get there, but for now it seems that we're already triggering it. So let's see. Why is this not happy? Okay, it needs an exception frame. Sure. It's unused. So. And save. Oh, and it doesn't return. Okay. Oh, okay, so if it doesn't return, we will never, it's, yeah, if it doesn't return, we don't get back to main, but this is just for debugging for now, so we add a while through here, or a loop, loop, and we, let's stop this because we figured out what was going wrong, so we can disconnect and we can close this and just use the regular run. Oh, unreachable statement. Yeah, okay, I don't really care about that. Try again. Oh, what's going on? Oh, it's still being, so the executable still used by GDB, so we quit it. Not only disconnect, but we also quit it. Sure. Try again. Yeah. Okay. So now it. Yeah. Okay. Now we see that indeed we end up in the hard fault. So our invalid instruction didn't cause a usage fault, but a hard fault. And seeing this, I already think I know what's going on, because this is a Cortex M4, and it is a bit more advanced than say Cortex M0, and the Cortex M0 only has the hard fault, and it doesn't have the usage fault and the MemManage and BusFault, so everything gets routed to the hard fault. But this chip has support for more specific faults, but you have to enable them. So let's go to the manuals and let's figure out where those bits are located. So let's open up these. Not sure which one I need, so let's open them all. Technical reference, user guide, and reference manual, processor. I think it's this one. Let's see. Memory model, programming model, exceptions and faults. Let's see, exception model, exception priorities is somewhere. UsageFault. Yes. Software can disable this fault. If it does, a usage fault escalates to a hard fault. So I think this is the case. So it's disabled. So we need to figure out how to enable it. And yeah, it would have been nice if that was linked, but no problem. So let's see where the registers are. Is this only the documentation? Stack alignment? No. Just click around a bit. Execution state. This is not. So let's see. It should be in the. How was it called? It should be in. I think it should be somewhere in this peripheral. So let's look for that one. In this. No. Factor, no. Exceptions. I have to reorient. Where would this stuff be? Instruction set peripherals. System control block. SCB, yes. HardFault status register. No. Configurable fault. So we need MemManage BusFault, and we want the user fault, something like UsageFault enable. Access instruction access violation flag. No. UsageFault status register. So this undefined. So so this should be set by our undefined instruction. But this is information when it already triggers. So we need another. Maybe this one. And aligned. No. What do we have? Control. No. NDNS. No. Yeah, just look at this. This we had. It's not it. This is not it. Escalate to ignore. Handlers for enemy, HardFault and faults escalated by fault mask to ignore BusFault. Ignore BusFault. No. We're not there. We're not trying to do anything with BusFaults, but we're trying to use a UsageFault. Ah, there is a priority thing. That's good to know. So CMSys has some functions for it. Maybe the Rust Hall will have similar functions. Don't know. Well, I think we already used one of them. Yeah. All right. This is the status. Ah, here we go. Enable bit set to want to enable. Yes, I think this is it. So here we can enable them and we can set them as pending. Yeah. Okay, I think this is it. So UsageFault enable. Yes. And this is located in the SHCSR. SCESR. Core. SCV. H. Yep. Then we want to modify, maybe read modify right. Yeah. And what do we get here? We get a function. It should be a t2 t. Sure. So we get a value, and we need to set a bit. Right? Yeah. Okay. And we need to set the UsageFault enables bit 18. So we order that in 18. Not sure about the precedence. No. Let's add braces because I'm not sure about the precedence, but all right. So this should enable it. And let's see what if this works. This we already have the UsageFault handler, the UsageFault exception handler. So if we have if we did enable it correctly, then we should see the UsageFault instead of the HardFault. So let's go ahead and try it out. Oh yeah, it's working. So okay. So okay. It's triggering again and again. So maybe the instruction pointer doesn't get so we get an exception on the bad instruction, and that causes the exception to trigger, but the instruction itself is not executed. So the instruction pointer is not advanced, so we don't step over it. So when we return from the UsageFault handler, we just end up back at this same instruction, and it triggers again immediately. So that's an issue. So we need to figure out how to update the instruction pointer. All right. Sure. I'm thinking of if I can somehow make this easier, because yeah, we could make this exception handler and make it what's it called, naked. So then we have to switch to assembly, and then we have a more guaranteed stack layout. Then we can modify the instruction pointer that will be on the stack. We can modify it to advance by I think 2 bytes. Most of the instructions are 2 bytes. That would cause us to jump over this instruction and prevent a second fault from triggering. But yeah, that will be hairy to do. So yeah, not sure. Not sure. Maybe for now we should be happy we got it triggered. So if, and that was one thing I didn't really show in the first video, or didn't really motivate in the first video. but I'll explain it here. So the whole goal of the stacking of the instructions is that in the end we have triggered all exceptions and they're all on the same stack, and with that then you can use a backtrace to show that all the exceptions are in the stack. Didn't really motivate that clearly at the beginning, but in the README I added this as some small footnote that, like the Pokemon and the Pokédex, the stack backtrace will show all the exceptions that were handled and in where we threw the next exception to show the chaining. So for now I'm happy that this works. We have to figure out a way to continue, or at least if you want to continue, then we should figure out a way to do that. But the end goal is to have them all on the same stack. So I don't really see a need to ever return from all the exceptions. So for now this is also fine. But that means that our debugging prints, so the hellos and the dones, from now on we'll only see the entries, so only the hellos, and the final end that was in the main we will also skip, because we'll never get there, and the done flag will also no longer be used. But as we saw in the previous video, the probe-rs run command also functions as a debugger. So when we hit a breakpoint, it also showed the exception stack. And the previous video I didn't really realize that, but that's exactly what we want. So let's add that. So instead of setting the done flag, we will set a breakpoint. Yeah, let me do that. I think that was in core. No, core. Oh, awesome. Okay. I think it was something like this. No. It's breakpoint, like that. So, yeah. So what do we see here? We have some unknown stuff. Exception frames aren't that nice. That's unfortunate. But okay, maybe look at it with GDB backtrace. So let's start the GDB server again and connect to it. Why is this taking so long? Seven backtrace. So here we got, yeah, this is what we want. We got the UsageFault, the SV call, the pend SV, and this was the issue that we had in the previous stream. The sysdig is missing because that we returned from it in order to trigger the SV pending. So in the sys_tick we set the SV pending, then we leave the sys_tick, and then we then the pending SV triggers. And at the time I thought, yeah, it's not what I want, but it's acceptable for now. But at the end I came up with a scheme that should work, that should allow us to trigger it with the sys_tick on the stack. And in order to do that, we need an additional exception. So the idea that I had was to trigger sys_tick as usual. In sys_tick, we don't set the SV flag immediately, but we call the SV call. It's a convenient instruction to do it, because this has a numbered argument that we maybe can use in some clever way. So we get two different SV calls. So here's the one with argument 1, and that triggers this one. And for now, this is just a single implementation, so it always does the invalid instruction. But what I was thinking is, well, I can make here a switch case or a select. Call a select? No, blanking. Match. A match on something. It would be convenient if we somehow get this number. Maybe it's in a register already. Would be nice. And with that we say, well, if it's a 1, then we will do the UsageFault. And if it's a 2, or maybe all the way around. So if it's a 0, then we will set the SV pending flag, so this thing. And yeah, with that we can change the ordering a bit. So we get into the sys_tick. The sys_tick will call the SV call. SV call will set the SV pending, and then it will return. That will cause the SV pending to trigger. And then we can continue the chain, because at that point we have the sys_tick. We went in SV call, we returned from SD call, and that triggered the SV pending. So then we have sys_tick SV pending on the stack. So that's what I want. That will be the order of priorities that's shown here. So let's see if we can implement that. And in order to do that, we just move the SV pending setting of the SV pending to this. And we copy this part to here, and now we call it with 0. All right. This is no longer needed because that will be in the final exception, setting the breakpoint. And now we have to figure out how to get the argument. So the numbered argument from the SV call instruction. So I'm not sure if this is conveniently placed in a register, or that you have to look at the instruction itself to get the number. So again, we need to mess with the call stack frame, and maybe we need the bare exceptions. But let's look at the documentation of SV call. What it does. So I think this would be It was under miscellaneous, I think. Where do we want instruction set? Yeah. This one. This one. So there is an intermediate. Is ignored by the processor. If required, it can be received by the exception handler to determine what service is being requested. It can be retrieved. Okay. Can extract the intermediate value by locating it through the stacked PC. Okay. So this sounds to me that it doesn't end up in a register and that we have to use the PC, so the program counter that has been stored on the stack, to retrieve the location of the instruction, of the SV call instruction, and then we decode that instruction. I think it's just simple masking of 8 bits somewhere in the 16 bits in order to retrieve this value. All right, I don't really feel like doing that, so let's work around it. Just like we did with the DOM flag, we will set our own. We'll just use regular memory to set this information, to get this information from one place to the other place. So from one instruction handler, exception handler, to the other exception handler. Yeah, that will be easier. So for now it will be fine. Yeah, we'll see if I can keep delaying the inevitable of dealing with the stack frame. So I will use ID, why not? Sure, doesn't have to be big. Oh, new 0. Yeah. And we can, let's see, here. So it doesn't really matter what this is anymore. So we will use idea to store a value in it. And let's store 0. And yeah, the ordering, can I copy that conveniently from somewhere? Yep, this. The ordering will be sequentially consistent. This is fine. And the same thing we'll do here. And then we'll set it to 1 instead. And in this we will do ID load with one argument. Where's the get? What is it? What's your problem? Oh, I think this is not loaded this right? No. Okay, yeah, so it's complaining that it's not exhaustive, so we add a default case, panic. Or, yeah, unreachable. And that will be it. All right. Oh, this is redundant because we already have that over here. It can be removed. Okay. So I think this should work. Let's see. So what I would expect to see is we see the hello world from main, the hello from Sysdig. Then we will see hello from svcall. Oh, maybe we can add the idea into the print. So let idea equals this, and we add ID back. ID back here, and we add it over here. I think this is supported also for the. No, maybe not. No, it doesn't. Didn't highlight proper, so, but maybe it is. Let's try. Don't know if this macro supports the inlined variables. We're done with this, so quit it. Yes. And we can just try to. Let's try to run it immediately and see if this works. Oh, it compiles, so. Oh, it compiles, but it doesn't work. Fine. It has support for this, right? Maybe it doesn't. No, it does. Okay, so it has support for the arguments. Okay, so we'll do it like this. Sure. Yep. Okay, so what do we see? We see the Sysdig that does the call 1, or the call 0. The call 0 gets done. That triggers the Sysdig? Oh. I see. So it still didn't work quite as I hoped, but let's work through what we see. So the Sysdig gets triggered. That triggers the svcall 0. The svcall 0, that should set our pending sv flag. So that has been set. And then we return from svcall, but it does not trigger the pending sv immediately after the sv call, and that causes it to be done in the Sysdig, and when we leave the Sysdig, then the pend sv gets handled. So I'm not sure if this is a limitation of the pend sv, or that it's just by design that it only works when going from exceptions back to regular code. But maybe we can tweak the priority of it to get it to trigger while the Sysdig is still active, still on the stack. Let's see if we can find something about this in the documentation, because I'm not sure. So let's see. I think this was the one with exception model, this one. So the pend sv, where is it? Interrupt? Oh, here. Profile supports 2 system level interrupts. It's permanently enabled. Okay. And the Sysdig is also enabled, but Okay, we have to look at the priorities of these things. I think we already had some code that does that, so let's see. So that should have been a lower number, so a higher priority. Okay. Can we find some more information about the SV pending? Maybe do a search in there. SV pend. No. Oh, pend SV. That's V. Still nothing. Okay. And this one. Okay. Yeah. No. Priority of the system handler. Okay, so they have priorities. And I thought in the previous video we checked that the priorities that they should be in different priority groups. But maybe that's not correct. So maybe do the same thing as with this 128. So to be sure, let's just add a bigger number, and then maybe I miscalculated the least significant bits or something like that, or maybe not all bits are implemented on this chip. I'm not sure. Let's try this. So this gives, yeah, okay, that was it, but that's okay, a bit weird. I thought I checked this previous time, but okay, for now it works. So we get the sysdig. Now we want the SV, the pend SV, but it doesn't trigger immediately. So yeah, we do it via the jump into SV call, return from it, then that will trigger the SV, pend SV. From pend SV we do the second call into SV call, and that triggers the UsageFault. So now we should have, yeah, this exception stack is a lot bigger, and it should contain the sysdig. It does. Pend SV, yes. SV call, nice. And finally UsageFault. So this works. Nice. All right. Nice. Then we can move to the next one. So we did the UsageFault. Can mark it as done. And the next one will be the BusFault. Yeah. And this one we already saw that this also has the set enable bits and the MemManage as well. So maybe we have to set them all to make sure. Yeah, that code we can just copy. But let's first add the exception handler for it. So we can copy that from here. So now this will be MemFault? BusFault. Okay. BusFault, and BusFault. This can be removed because we no longer use it. The breakpoint, sure. And this one is this one we should add it to trigger the BusFault. So this is to do for now. To do this one, and then we can let's first add the bit. So we need to set it as well. Yeah. This register. What document was it in, or is it still open? Maybe, if we're lucky. Doesn't seem. Alright, here it is. So it's 18, 17, and 16. So let's enable them all and be done with it. So 18, it was 16, 17, 18, 16, 17, 18, right? Yep. So that should be enough to enable the BusFault, right? Yeah, BusFault. We're working on the BusFault. So let's see how we can trigger that. I think that was somewhere here. Only one hit, so probably not. Oh, it has space behind it. Does that change anything? No, still only one hit. Let's look through this document. BusFault status register. Where was the summary with this one? This one. Yeah, this one. BusFault. This is what I was looking for. So the BusFault fault handles memory related faults. Okay. Other than those handled by MemManage. Okay. Typically these faults arise from errors detected by system buses. The architecture permits an implementation to report synchronous or asynchronous bus faults according to the circumstances that trigger the exception. Software can disable this fault. Well, we enabled it, so yeah. If we not enable it, we get a hard fault. But that's not what we want, so we want to enable it, but so it's faults that are not handled by MemManage. So what is handled by MemManage? So memory protection unit, fixed memory constraints. Alright. So, okay. Let's look around for some more information, because this is a bit, yeah, so it's talking about imprecise and asynchronous faults. I think, let's see, I think there is maybe that we can do some unaligned memory accesses. Maybe those will be covered by the BusFault. Because I think writing to flash would also be cached, but I think that will be the MemManage fault, because that would be a system region that the flash region should be should have priority of permissions that it can only be read and not written. So, but I think that will be a memory MemManage fault. So for BusFault, yeah, maybe a misaligned read or write, misaligned read, is something that we can use. I don't know. Load multiple. Yeah. Load multiple. Nah. A fault condition can be a bus. No. I want to know how to trigger it. Maybe, yeah, maybe that's an idea. Just look at the BusFault had the status register that showed the specifics of the fault. So maybe that will give us some hints on what fault it will handle. Yeah, so the status register, this one. So it has let's see. It has floating point, lazy state, preservation. I think that's something to do with saving floating point registers to the stack, but only when your interrupt routine uses floating point instructions and needs his own set of registers. So that's an optimization, but don't think we're going to use that one. This also seemed to be something related with interrupts and maybe an exception during the creation of an exception frame. And this is the return of an exception frame, so imprecise data bus error. Instruction bus error. That's it. Imprecise data bus error. So it points to the exception that caused the problem on prefetching an instruction. Okay. Yeah, not getting anything useful out of this. So, oh, here, the UsageFault, but that's the one we already did. So this one has, yeah, okay, unaligned access fault. So this one will also catch unaligned accesses. And the divide by 0. So, yeah, the user, yeah, okay, UsageFault is just a lot of stuff the user can do wrong. So divide by 0, unaligned access. But this BusFault is a bit more hardcore in that it seems to trigger in really specific cases. So yeah, this all has to do with exception frame creation and unstacking. don't know how we can trigger that in an easy way. Imprecise. Data bus error. Data bus error. What is a data bus error? Instruction bus error. Oh, okay. I think they're talking about the. So most of the it's common that processors have separate buses, so separate channels to fetch data from memory for the data that they want to use to process stuff, and for instructions. So most of the time they also have separate caches, so an instruction cache and a data cache. But this chip doesn't have cache, I think, but I think it's still modeled as if there are two channels. So a data bus, I think the data bus is just the bus it uses to fetch data, so for loads and for stores. And the instruction bus is just the bus it used to fetch instructions. So how do we... Maybe we can try to fetch data from a bad place. I don't know. Sounds a bit like a MemFault. I was thinking maybe we try to execute instructions from a memory location that is a peripheral. So don't know if that will be catched by the system, but that would be more like a memory violation. So we try to execute non-executable memory, but I don't know. So is there anything more? So this is the MemManage. So MemManage will deal with data access violations. So these are violations. Fault occurs on any access to an NX, VX, N region, even if the NPU is disabled or not present. Okay. So that's an execute never, I think. XN execute never. So I think this is the... Yeah, I think this will trigger if you try to execute like the registers of a peripheral as if they are code. But I'm not sure. Maybe we can try this and see if we can trigger the MemManage fault instead. And we have to look for the BusFault. Yeah, we have to find another way to trigger the BusFault, but yeah, I'm not sure. So for now, maybe try to execute a peripheral as if it is code. So let's do that. So in order to be able to see the the priorities here, also missing still the new stuff. So let's so I think 0 is the default. So let's make this one a little bit less high priority, so the UsageFault. So we have still room left to trigger other stuff. And let's continue to add. Let's decrement another. Yeah. like this. So we go in steps from 46. Yeah. Okay, so that was the priority. The exceptions we're going to trigger will have the default priority of 0. Maybe we make it explicit just to be sure. So let's add them anyway. So we actually want the BusFault, but BusFault. But for now we try to trigger the management. Okay. It's a bit a different name, but sure. And let's have them at the highest priority. So we try to trigger any one of these two. So BusFault or memory manage fault. We'll see what happened. The BusFault already had an exception handler, so we add one for the memory manage fault. Manage. It's called. No, it wants memory management. Okay. Sure. And let's update this to do. So what we're going to do, we're going to call into a memory location that is not code but is a register. So peripheral block. So I'm curious what would happen. I think the chip should be designed that those regions are marked as never execute. Maybe we should look that up. So what does this mean? Because I thought it would be execute never. That sounds like something that could be possible. Yeah, execute never. Prevents instruction as means prevents instruction accesses. Okay, yeah, sure. So, oh, is it even declared somewhere where stuff? Yeah, it is. Okay. So there are known regions that are execute never. So yeah, we can just the bit bend. Okay. Cool. Yeah, just jump into here. Why not? So this is where the bit bend and bit bend alias. Yeah, this is a feature. I never really used it, but it's a feature to address individual bits, typically in GPIO registers, or maybe other registers are also supported. So you couldn't do, well, it's a specific addressing scheme, so you can do atomic bit masks in those registers. So atomic setting and updating bits within a register. It's really convenient. Yeah, but I never used that, or maybe some library did use it underwater, but I never used it myself directly. So what do we want to do? We want to create an instruction pointer out of thin air. So I don't think Rust is going to be really happy with this, but we have to yeah, I have to think about how we're going to do this, but I think it's just let's see, that, and this will be func xn execute never, is going to be of type fn pointer to nothing. I think this is how you do it. And then we just take this and we assign it. Don't know if it's this easy, but yeah. And then so we use an as. Oh, maybe we can just. Oh, we need a pointer here, so it will be an const. Maybe like this. All right. Sure. And then we can call it. Call expression requires function. I need to deref it. Then call it. Maybe do this like this, maybe. Yep. Okay. So this should be it. Okay. Let's see. I don't know. Let's run it. Let's see what happens. HardFault. HardFault. So we go into the UsageFault. Then we do the stupid thing of calling into the non-executable of non-execute never memory, and we get a HardFault instead of our BusFault or MemManage fault. So something's not right. Okay, and maybe here we get into trouble because we're trying to stack as many exceptions as possible, but maybe the chip doesn't allow us to have this many exceptions in exceptions, and especially the fault, the real fault, so UsageFault, HardFault, MemManage. Yeah, those are typically like something's really bad happened, so it's quite possible that the chip doesn't support stacking those or preventing you to do that. So let's see what happens if we do this in an earlier exception, or maybe just directly in the main, to see if it has something to do with the stacking. So somewhere around here maybe. So I copied the code and added it to the main. So now we just see if what happens if we try to trigger this exception from the main, so there are no other exceptions beneath us. And I would expect that this should trigger the MemFault or the BusFault. Also the HardFault. Okay, so there's, but also the UsageFault. What? So it triggers the UsageFault. Ah, okay, and okay, yeah. So triggering a UsageFault within the UsageFault, that's just an HardFault immediately. That's like the Intel chips of the x86 has a similar thing, like triple faulting or double faulting. That's yeah. So the chip detects if you have an exception within the same exception, then yeah, it's just game over. or not game over, you still get a hard fault, but okay, so why is this usage fault? I know why. We're calling an instruction, we're calling an address, we're just taking a number, saying it's a function pointer, and we call it. But the ARM instruction pointers, they encode this is a weird feature, but they encode the instruction set. So this chip doesn't support multiple instruction set, but older chips, they had different modes. So they had an ARM mode and they had a dump mode. The dump mode was an extension, and that extension has taken over, so now these chips only have the extension, no longer the ARM mode. But they did it in a clever way, so you could intermix those different instruction sets, and you could use them at the same time. And the way you told the processor what instruction set it should use to interpret the bytes that are coming into the instruction fetching, it used the lowest bit of the instruction pointer, of an instruction, use the lowest bit of a call instruction to signal this is calling into ARM code or is calling into dump code. And if I remember correctly, this would signal we're calling into ARM code because it has the bit not set, the lowest bit. And this chip doesn't support the ARM code. So it doesn't support ARM code, so that will be a usage fault, because you as a user doing something stupid, you're trying to call into ARM code, doesn't work on this chip, so it gets a usage fault. But in our usage fault, we're doing the same thing again because we copy pasted it, and that would trigger the exception again. So let's see. I will change it at both places, so we make it the least significant bit, we make it 1. So I changed it here and also in the copied thing, so here, and we try it again. I think this should fix it. Yeah, okay. We get a panic, so interesting. So all right. What's going on here? Misaligned pointer dereference. I get the panic over here? Okay, something's not cool. Oh, am I creating a pointer to a function instead of a function pointer? Is this not necessary? Oh, maybe it's something different entirely. Okay, so yeah, I don't know, does this work? Non-primitive cost. How should this be done? So the fn is apparently a type that can be used on its own, so this must be a function pointer, right? But pretty cool that Rust catch this for us, because yeah, must. What's going on here? So I just want to call this address as if it is an instruction, as if it is a function pointer. So how do I create a function pointer out of thin air in Rust? I don't know. So if non-primitive, yeah, invalid cast, sure. Okay, yeah, so maybe this isn't allowed. Maybe we need to transmute. Let's see. Like there is a way to go from okay, that's the problem. So there is a way to go from pointer into integer, but there isn't a way to go from integer back to pointer, I think. The only way to do that is, or not the only way, but a way to do that would be with what's it called? Transmute. But that's, yeah, that's some dangerous stuff, but yeah, what can go wrong, right? We want to crash the system, so let's see. Transmute. I think it's, where would this be? Core mem? Core mem transmute? Yep. Okay. How does this function look? I think it takes 2 arguments. Oh, a source and a destination. So as a source we just have the integer. As the destination we will have a function pointer. Okay. Compiler seems to be happy, but I'm not sure if this does what I want, but let's try it. So yes, we get the memory management. Is that what we expect? Yeah, I think that was what I expected. Yeah, because so we're trying to execute this this memory location as if it is code, but it is marked as execute never, so this would be an access violation, and access violations are managed by the memory management. So okay, this does at least this is something, and we get the memory management, so that's cool. So 2 things. First, this is not a BusFault, so we still have to figure out a way to trigger the BusFault. And second, I'm curious if the whole rambling thing about the ARM instructions and thumb instructions is still correct. So let's change this to a 0. So now it should be. It should indicate to the system, okay, I'm going to call code, and it's an ARM instruction format, not a thumb format, and the chip should, should throw an exception on that, I think. So let's try that. No, it does not. Okay. So now I'm really curious. Does this even do what I think it does? So let's edit here in the UsageFault. Maybe remove the prints. Make this the UsageFault as simple as possible, and then we can use debugger to show the instructions. Because I'm really curious what instructions are generated. Would expect this. Well, what would I expect? maybe this is stored somewhere in Flash, then it's one instruction to do a relative load and then another instruction to call with a register. Expect that would be the maybe some prelude and some entry and some exit stack stuff. What's it called? Prelude and exit or something like that? Not sure. Oh well, for now, let's compile this. Just compiling would be enough. So cargo build, load the executable into the debugger, into GDB, and then we can do a disassemble of UsageFault, but I think it has a trampoline part. Yep. So we actually want this thing. This thing. Yeah. Okay. So what's going on? So it loads the number into R1. R0. It stores. What? Here it's getting called, but what's going on here? It stores. It stores it into an intermediate variable. Because this is a debug build, so at least I think this is what it does. So this is on the source and this will be the destination, I think. So it stores relative to the stack, so it stores the value on in an intermediate variable in memory that's never been used again. Yeah, it's just a debug build. So this should do what I this is pretty much what I expect it to be. So still a bit puzzled why. Why it's not. Yeah. What's going on with the least significant bit? Well, oh well. At least this works. So we are able to trigger a memory management fault, right? Yeah, memory management. So, all right, but this is a memory management fault from the main. But we wanted the memory management fault, or we wanted the BusFault, but we got the memory management fault. But for now, let's continue with that. We want to trigger it from our last exception. So where are we? It was in the UsageFault. So we want to go from UsageFault. Okay, I'll add the prints back for now. The UsageFault, and then into the memory management. Let's see if this works, because what's going on? Oh, the debugger is still running. So let's quit it and run this one. Okay, so this works. But it's the memory management fault and not the BusFault. So yeah. Take a small break. See if I can Can I pause it? I cannot. So I'm back. Where were we? Yeah, so we were able to trigger the mem management fault, but not the BusFault, BusFault not yet. We looked at the documentation for the BusFault. This one, not this document, but Bus. Yeah, this one. Memory related fault for an instruction or data memory transaction. Okay. But we didn't really figure out what that meant. Oh, bus error, yeah. During instruction prefetch, during lazy floating point state preservation. Ah, okay. So if these are all the if these are all the possible reasons for a fault to happen, then it's pretty limited. Yeah, and this is the instruction access violation. This is the one I think we triggered. Don't know for sure, but it might be possible. So yeah, I'm not sure when these happen, because for instance, say we corrupt the stack pointer in order to get exception during exception stacking. We corrupt it. Maybe we can make it unaligned, but I think that would, yeah, maybe not. I'm not sure when this would trigger the thing. So bus error. Maybe search for this, or how many. Oh, there's still a lot of bus faults in this document, so maybe look a bit more around. A stack push. If a bus fault occurs during stack push. Okay. So it really is when the exception frame is being built, if the stack frame is being built. What is this? Configuration and control register. Enables handlers with priority. Enable handlers with priority -1 or 2 to ignore data bus fault caused by loads and store instructions. Ah, okay, so we can even ignore bus faults when you're in a super high priority, so enemy or hard fault or enemy. Sure. Unaligned trap, no, okay. This is not it. Nope. think so. BusFault exception active now. Floating point. Let's see. Yeah, this is what we read before, but BusFault and unstacking from a return from exception. Cast one or more BusFaults. They're still talking about the BusFault. I still don't know what a BusFault is. I mean, this is the BusFault exception, but how do I trigger a BusFault? I mean, these bits indicate when the BusFault happens. So during stacking or unstacking, or during the floating point lazy state preservation. But it doesn't tell me what the BusFault is. So instruction bus error. No. BusFault address. So contains the address of the location that generated the BusFault. Okay. When an unaligned access faults the address. Well, okay. When an unaligned access faults, the address is in the BFAR. Requested by the instruction, even it's not the address of the fault. Okay. So here they're talking about an unaligned access. So maybe it is covering those. What are these bits? Floating point, context control. Nope. Yeah, back to the beginning. So this is not really helpful. Maybe this one also has a lot of matches for BusFault. So let's look around. BusFault. Yeah. On exception entry. Yeah, whatever. Return, imprecise. Imprecise BusFault called by explicit memory access. Dus it should be possible to trigger a BusFault with a memory access. Yeah, but it won't be an access violation, so there's still other things that can happen. So yeah, and the UsageFault is for unaligned stuff. So when does this happen, man? Bus error. And this is, I think, the keyword we need to find. Bus error. Okay. Bus error. Only 9 hits. shows the status of the bus as a result of instruction prefetches and data accesses. No. Okay. An instruction fetched. Yeah, okay. Cannot generate it. Okay, so this has to do with debugging. Not interested in that. Bus error. Yeah. Still not sure what the bus error is. Maybe this has something to say about it. Nope. Maybe this one. Fault handling. Faults are a subset of exceptions. Faults are generated by a bus error. Sure. Oh. Bus. No, this is what we're already seeing. Imprecise data bus error. Really wonder what that one is, man. Imprecise. Bus error occurred. Caused the fault. Yeah, I don't know, man. The manual has nothing to say about it. Only that it can happen, not what triggers it. So maybe just Google it. Bus error. I'm going to try Stack Overflow. Yeah, just look. Let's see. So yeah, this is not really related. I think not really relevant for this, for what we're looking for. Oh, segmentation for SigBus. There's also a Linux error code. Yeah, so this is, I think, the same documentation we're already seeing. There are several reasons why a bus error can occur. For example, when the processor attempts to access invalid memory location. Invalid memory location. The device is not ready to accept the transfer. Okay. An unprivileged access, a privileged access. Okay, so maybe we can just read in, like in memory that is not mapped in, invalid memory location. Maybe we can use this. So there was a document that had the memory locations. What document was it? This one? Not sure. Yeah, that's the bit branding. That's the that was the bit branding was the memory location that we used to trigger the access violation. Memory registers, memory model, address space, system address map, this one. So is there a location that is not used or not invalid? But yeah, what does that mean? Invalid memory location. Invalid memory location. So we can try to read in this memory location, but at the end of it, so typically maybe the SROM. Let's see. Yeah, let's try that. Let's try to read from some location that we know will at least have no memory mapped on it, so the chip doesn't have RAM there, but maybe it's aliased or it wraps around or whatever, but we will see. So let's pick a target location. Let's go for let's go for this first block. So typically, according to this, it has ROM or flash memory, and I think the specific chip that I'm using maps its flash there, or maybe you can select it so you can have different. So some chips have support for some bank swapping feature where they can alias the SRAM or the flash, so the RAM or the flash, and they have a separate region that can be swapped to alias one of them. And I think this chip also has that, and normally it's just flash. So then you can write your code as if it starts from address 0, and then but in the end it ends up typically, I think, in the 8 or no 08 is it most of the time. Never mind. Let's read here. So we're going to try to get a BusFault. We will take this address. Let's test stuff in the main like we did before, so around here. So let's make a variable that will contain the pointer so that we can dereference it. We know we want this address. Let's make sure it's properly aligned, so let's make it end with a C. We store this in for BusFault. BusFault. And this time we Yeah, let's also immediately do the transmute stuff so we don't get that wrong. We want to create a pointer const. So we want to, let's see how we do this. We want to create a pointer to that memory location as a U32, whatever, doesn't really matter. It is aligned. Is this allowed already? I don't think so, right? No. But can we do it like this? I don't think this is supported. Oh, it is. Okay. Sure. Then this isn't necessary. We just do it like this. And we do df of this. Like this. So this is unused, so sure. Let like this. Okay, let's see what this does. So this didn't do anything. This didn't trigger anything, at least. So it doesn't seem to, yeah, doesn't seem to care that we're doing the memory access here. So yeah, okay. Let's try another address, because maybe in the device space. BFFF, yeah, sure, why not? So let's try something here. Still nothing. Does this, maybe this gets optimized away, but let's see. Can we make this a volatile read or something like that? Read volatile, like this. Just to be sure it didn't. Nope. So it doesn't really seem to care that we're reading from this memory. Maybe we write to it. I guess this takes an argument. What do you want? Oh, sure. Okay. Don't know about this, but still not a problem. Okay, weird. Maybe back to this location. Yes. All right. Cool. So we triggered the BusFault. All right. So we got our primitive. Let's add this to the stack. So nice. This we want to use it over here. So this is 8 for right to in to call BusFault. This was the MemManage. So from the BusFault we trigger the MemManage, so this can be removed. Call into execute never to call what's it called? MemManage? Memory management. I don't like that name. I just want to. I think we have it here. MemManage. Fault. Okay. All right. Do we get the full chain now? No, we do not. Right. We get the UsageFault into the BusFault. UsageFault into the BusFault. But then we go into the HardFault, and I think this is a priority issue because the priorities are still equal for both. So we need to update this. So we need to give. Okay, so first let's give us some more space to work with. So let's try to so okay. So I thought that 2 should be enough, but apparently it's not. So let's add a constant that we can modify, we can tweak to get the step size that we need in order to have separate priorities. So step, for now I will use 2, but we already know this doesn't work. But at least 3 times step. Oh, minus. Then we can tweak what step should be and see what is the correct value. So this didn't work the previous time. What's complaining about? This should be 8, I guess. Yep. Okay. So let's try again. This didn't work the previous time. So from sysdig we enter HardFault. Okay. Sure. So I think, yeah, it doesn't really matter why that's the case, but let's increase it. That's still not enough. Make it 8. So we keep doubling it. Yeah, okay, so keep doubling it. Almost. What's going on here? So we successfully end up in the PendSV, but we fail to jump into the UsageFault. So still not enough? I don't know. What's going on here? So this is enough, is it? Yeah. UsageFault, BusFault, memory management. So apparently, yeah, don't know, maybe this chip doesn't support that many levels, so least significant bits are not set, or yeah, don't know. Maybe the default values for the subgrouping is different. Let's check that. Let's check what that is, because this is a bit strange. At least we got it working, but this isn't what I expect. Yeah, this isn't working how I would expect it to be. So let's look into it. So somewhere in this document there was a mention about the priorities. It was in the SCP, I think. So what document is that? This one? Yeah, system block. Control? No. Application. Control register. Somewhere here. Priority. This is priority stuff. No. UsageFault. No. 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 Where is it? Let's see. Oh, this is really short. So exception and priorities. That's something to do with a group. System control block. Instructions, no. Somewhere around here. This exception number, exception priorities and preemption, this one. So number of priority levels. So yeah, we need this to be at least 16, otherwise we don't have enough. Yeah, don't have enough priorities, so each can preempt the other. So let's read this. So so yeah, this is implementation defined, so it depends on the chip. So maybe this chip doesn't have enough bits to do that. So okay, where do we find that? Yeah, so this is the pre-group, so priority group. Okay, so maybe we should just print this value. So the pre-group in the A and all right. Oh, okay. Application, and where is this? It's in the, yeah, okay, it was the SCB. I remember from the previous time, so this one. Okay. Core.scp scb dot, yeah, that was the one, AE. This one, and then we want to read this. We just print it as hexadecimal. So let's do that. AERCR. I think this is hex. Like this. What did we get? A lot of zeros, but yeah. So the least significant, yes. So the least significant 16 bits are all 0. So these are all 0. This includes the pre-group, and the pre-group, as we saw before, when it's set to 0, it has a subgroup priority like this. So yeah, maybe it's just the chip that doesn't support as many levels. But I wonder how you get to maybe you can query this, or maybe this is just specified in the documentation of the chip itself. So okay. But do we have enough? That's the question. So we have 16, and 16 divided by, oh, that's yeah, okay. So it goes in steps of 16, and we need 16. Yeah, that's enough. Okay, nice. So we have enough. We have enough so we can continue stacking the exceptions. But all right. So what did we do? Because I think this is a good place to end it. We have maybe clean up the text a bit, because I don't really like how it's presented currently. So let's call this main. Oh. And then we call each thing, we just call it what it is, because we no longer see the DOM, that we can remove this and this one, and so simplify this a bit. Yeah, maybe, do I want to show this, or do I want to hide this? I don't know. Let's see how it looks when it's not changed. So BusFault, this can be removed, and this is currently our last exception. But yeah, it's trivial to trigger the HardFault. I think we can just do this again, because if we trigger a MemManage fault while we're already in the MemManaged exception handler, it will HardFault. So, or I believe it will. So let's do it like this for now. We add the HardFault thingy. Okay, this is no longer needed. All right, this looks good. Sure. Yeah, this can also be removed, and we can fully remove the done flag. It's no longer being used. And this one as well, sure. Let's see, how does it look? It's not happy. Done. Where are you? Oh, okay. Yeah, so the non-maskable interrupt, that one is still the exception we still need to get to, but for now we'll have this. So yeah, maybe I'll just remove this entry. No, I'll leave it with the numbered suffix. That will be fine. So yeah, here as we call one, and I will, for this one I will add the exit as well. I don't like it because it will not be symmetric. Maybe I just move this. This is what I will do. This one I will add here and here, but I will let me clean this up like this. I will add a couple of spaces here, so to indicate that this is a special one. So what do we get when we run this? So we get the main, we get the sysdig, then we get the extra SV call to trigger the pend SV that we I also like, maybe we can indent it all the way to show the stack depth. No, it doesn't really matter. Pend v, SV call, UsageFault, BusFault, memory fault, HardFault. Okay, we got a lot of them done. Okay, I'm happy with this presentation. So that is save this. We can update the README. So we did almost done. We did these three. All right, the list is getting smaller. So yeah, that will be I think this is a nice place to end the video for now. One final thing I want to see is the stack trace in GDB, so I will run that one more time. So we start the debug server and we will start GDB itself, and then we can just connect to it if it's loaded. Yeah, okay. Target remote 1, 2, 3, 7. Yep, and then the backtrace. All right. So we got. Oh, it's even has more. Right, now there's everything. So we got our main, all the trampoline stuff in between, kind of funny. But okay, we got our main, we got our sysdig, we got our pend SV, we got our SV call, we got our UsageFault. This one has no, only has the trampoline, but okay. Then we have the BusFault, Yeah, UsageFault, BusFault, MemManage fault, HardFault. Nice. Nice. Okay. I'm really happy with this. So next time we can try to trigger the NMI and the reset. Yeah, reset will be yeah. Is that really an exception? I don't know. We have to see what the manual says about it, but yeah, I mean, if we trigger this one, we just get into a loop and we start all over again. But that's yeah, I think that will count as the trigger. And then we end back up in main. We lose our stack, but we end we complete the cycle. So yeah, that sounds like it's doable. And the NMI, yeah, we have to look into how we can trigger this. And yeah, maybe we have to look at the debug monitor just for completeness, because we skipped it because in the previous video we found out that yeah, the debugger of the probe arrest that we're using also hooks into the debugging features of the chip, so you get a nice exception as we see here. So oh, where do we see it? Oh, we don't. Oh, that's true. We have to add it back, because we now get into the HardFault, and here we want to add the breakpoint. So this one is like this, and now we get oh, that's not what I wanted. And this will complain. Yeah. Okay. Quit. Yes. So is this still what we had? Yeah. Bend, call, UsageFault, BusFault, MemManage, HardFault, and here we get the probe arrest that triggers that catches this breakpoint and shows a bit of an exception frame of a call stack, but not as nice as GDB. So this one is more complete. But yeah, that one is still then yeah, maybe we can still try to include this, but then we will lose our debug abilities. So I will save this one for last. So next time we'll start with the NMI and the software and the chip reset. But for now, this is yeah, this is a great place to end. Thanks for watching, and see you in the next video.